All right, so we've been mingling here, getting started on the pop quiz for this month. As always, Mike Driscoll providing some tricky brain teasers and basically terrible examples of code. But they're good examples of, or good ways to highlight the nuances of the way Python language operates. So we've got a pretty short one here. We instantiate a variable number with the value of 5, and then we distract the audience by defining a list via list comprehension, passing for number in range. And so the distraction here is in the scope of this list comprehension. We are then iterating on the value number and storing it into the position it's at in that list. So
Yeah, that would be the evens, or the odd numbers between 5 and 40 and 49.
right,
That's what
because we're
that range.
spacing it, we're incrementing by 2.
Right.
And so we look at that and we say, oh, well, obviously it's got to be somewhere at the end there. So maybe you don't understand how we increment through a list, and you see 50 at the end of it and say, oh, it's got to be 50. Then maybe you're a little more clever and realize, oh, it's actually ended at 49. But then, yeah, it seems like realistically we're just getting another scope problem thrown at us by Mike. But as always, we're gonna switch over to a REPL just to verify that that is in fact what we're looking at here. And so
Ripple?
REPL.
Read, evaluate, print, loop.
Bruh.
Okay, so number equals 5. Lots of numbers equals number for number in range 522. So let's see what we got. And if you guessed A, 5 is correct. So basically, having number in that list comprehension, like as soon as we're done with the list comprehension, we're out of that scope, right? It's like the long and short of it, I think.
So do you have posted something where it looked like you got something different in the chat?
Really,
Yeah, was that, sorry, was that Robert asking me?
No, it's Nitin.
Sorry. It was something Robert said that when he was guiding Elliott, he was saying that a list comprehension is the same as an unrolled for loop. So I've put the code into the chat, which is the unrolled version using a traditional for loop, but it's not correct. This is where the trap lies. So, Rob, you were right the first time when you questioned scope. A for loop is
Actually, I caught myself that a for loop doesn't have its own scope, but a function does.
Correct. Yes, dead right. So, the for loop operates in the scope of the wider code. So, if you happen to be in a function or you happen to be in the main global scope, wherever you started your for loop, everything takes place in that scope. Whereas with the list comprehension, it forms a mini scope of its own. So Elliott, you were quite right to suspect number. So number equals 5 is number in the main scope, let's call it. Whereas number inside the list comprehension is in a different scope. So it's a different number. Right. If it were possible, and it's not, but if it were possible to actually debug that by stopping in the middle of the list comprehension, you would find that the ID of number inside the comprehension is a completely different area of memory to the ID of number equals 5.
right.
So it is a nasty little trap.
Well, you shouldn't be writing code that where you mask the
You have one scope
Agreed.
that masks shadows the value. You know, a linter
Well,
should give you a death penalty offense for that.
Yeah,
You're correct. You shouldn't be writing code like that, but you also should be able to detect that someone did a bonehead error like that.
Well, sure. But it works this way in Python because for loop isn't its own scope for historical reasons because you wanted to inspect the value when you bailed. But there's a lot of languages, I think Java, I mean, basically almost every other language doesn't work this way. So if you sort of take these Pythonic principles and go elsewhere, you get burnt. So, you know, this is not a generally good portable coding style.
Do other languages have list comprehensions in them?
There's a few that do.
Well, that's not really the issue. The issue is that a for loop should be its own scope in theory. And in the original Python 1.x, it was a hack because people wanted to be able to inspect the value of the loop variable when they bailed out.
So Dean just actually went over the for loop case. If you actually do a for loop, it works like it would in Java.
However, the point is that the identifier number is being used in two different contexts, and that's the point that you were making a moment ago. That's foolishness, and it's going to trap all sorts of people, and that's why Mike put this question together in an attempt.
It's like, I mean, it's one of those things. I have literally I've never done this. I've never declared a variable and used an iterator for used an iterator. I'm sorry, a variable generated from an iterator that is another declared variable. So it's like, oh man, who would think to do that?
There's a number of
I think
no, but it's not who would think to do that. It's who wouldn't think and who would do it without thinking and then have to pay the price.
Yeah.
There's a number of formal Python certification tests. There's like an entry level, there's like a journeyman level, and there's like an advanced level. And all those tests, they love this idea that same trick where they have the scope change to throw people off. So I've seen so many of those scoping issues that I automatically look for that.
Well done, everyone. Mike Driscoll foiled again. All right. Just to open the evening with some machine learning jokes. This is your machine learning system? Yep. Pour the data into this big pile of linear algebra, then collect the answers on the other side. What if the answers are wrong? Then just stir the pile until they start looking right. So hopefully we learned a little bit tonight about how to stir the pile just right. Welcome everyone. It's April 3rd. Start of quarter 2, 2025. All right. So it's April. That means the beginning of quarter 2. This company or this group is sponsored in part by a company I run. And I kind of use this as a practice ground for updating on what's going on every so often with the company. So this is the quarter 2 update, aka the frymatic update. Frymatic is my marketing handle on a bunch of not to be trusted social media outlets like GitHub and SoundCloud and LinkedIn and Discord and Twitter and stuff like that. But I'm back here at Shea Twinkles, Dr. Tanim Islam's place here in Livermore. I started the year there. I took a brief jaunt out of state and I'm back here now. We have been spending weekends going out to the farmer's market and meeting people with the help of the SacPy mascot Twinkles. As you can see there, Twinkles is the total charmer. That's the doctor in the foreground. We've been cooking up a storm. He's made it through the chicken nuggets. This is my own recipe. Even one of these days we'll do a cooking show edition of SacPy. In that jaunt out of state, I made it out to Colorado. I was left with a number of puzzles to deal with. Some of them were snowier than others. I think I'd solved the snow one pretty well by the end. There's probably a picture of that other puzzle being fixed, but that's neither here nor there. One of the things I did while I was out there was I continued my stream of DIY sound boxes. This one I made out of the packaging of a simple Walmart condenser mic and some toilet paper and paper towels. And I used it to record my first narration of a book on Audible. It's a biography on George Peabody of Peabody Awards and the Peabody Library and the Peabody Institute and whatnot. And that's been up as of March 3rd. Literally a plural amount of copies have been sold. We're we're very proud of our 4.3 million Amazon ranking here in Brazen Studios. Good times. Also, I got started on the computer vision referee project that I've been talking about these past few weeks. It's about darts. A referee for darts. My friend had put together a darts scoreboard on Google spreadsheets and played with some of his friends over the pandemic. And we sought to make that a little bit more in depth and a little bit more of like a streaming game. So here's the setup in Livermore. As you can see there on the laptop in the picture, I was playing over Zoom with my friend. He had his camera pointed at his board. I had the camera pointed at the board on this end. And that's about what it looked like in the stream. Working on getting some other friends' dartboards on the network. Hopefully we can start playing webcam darts a little bit more regularly. And so that's pretty much the breakdown there. That was actually on OBS, but the aim is to get this punched up a little bit more on Streamlabs, which is a fork of OBS, and use some Logitech webcams because Streamlabs is a Logitech property, and make it a little bit nicer there. That's a Python-based program that I used as a scoreboard to drive some graphics on Streamlabs. So having cameras pointed at dartboards begs the question, can we do something interesting with computer vision? And I think maybe yes. Here we can see the detection of a newly thrown dart in a board. That's just a differ using Python image library. And I think there's maybe some interesting opportunities to work with shadows and triangulating a point of intersection on a board. And so my thinking there is if we can figure out interesting shadows, we can use fewer camera angles. And so I got to working on some novel lighting opportunities. Obviously, this is the very early janky stuff. We got banana clips holding together connections on a single LED and a Noah's Bagels cup with some tinfoil on it. Some hand sketches of what I was kind of hoping for, something a little bit more solid. And some mock-ups in, I think this is SketchUp. Got to 3D printing it on my friend's Prusa. And there's a, mock-up of a light fixture. Obviously, this one's not going to work, but it's been fun kind of prototyping. Another one of the issues I ran into was the lights I had available were just not bright enough to make any sort of meaningful shadows. So been working that out and found some fairly bright diodes. I think I still have some spots in my eyes from looking a little too directly at one of these yesterday. And it seems like it's going to give me some nice shadows to calculate on. I've also been spending some time hanging out with the San Diego Python group on the weekends. DN and I think a few others from this group tonight hang out there. Diane Chen, who's not with us tonight, she's still alive. She's just not in attendance. But she's one of the organizers of that group. They meet over Discord on the weekend and do something of a study group. It's pretty fun. It's freewheeling, a bunch of people working on some interesting projects. No real schedule. It's just sort of every Saturday, people get on and BS. And you can find them at, wait, is it really Sandy Python? Oh no, San Diego Python.org. Yeah. Maybe I can like drop the Discord in the chat. Yeah, there we go. Up next, we have the main event tonight. We've got PyTorch Generalization with Elliott Miller. All right, Elliott, the floor is yours. Take it away.
Okay, so this project stemmed from my love of deep learning, machine learning. I have late night insomnia sessions where I will just look at prominent researchers and see what kind of work they do. One moment, let me get my screen share up. Okay, everybody can see that. So you know a bit about me. Okay. A bit about me. I currently am I've been a machine learning engineer for 10 years. I previously worked for a company called Black Sky. I still have some of their merchandise, and yeah, it was really fun. I worked there for 8 years. I did NLP, computer vision, and time series analysis. I actually did a lot of other stuff, almost basically everything. Um, I now currently work for a telecommunications startup, although I don't know for how much longer because I'm actively job searching. Although that's not why I'm here. Um, in a past life, I was a physicist that had interest in antimatter and quantum computing. And I actually am growing an interest in quantum computing because I think the stuff that IBM is doing with Qiskit is amazing. So I'm going to just talk about the problem I'm going to tackle, which is generalization. More particularly, it's why generalization fails in machine learning. I'm going to give a brief overview of machine learning and talk about why that's important. Then I'm going to cover some relevant papers that I highly recommend reading. I'm just going to get some high level concepts, although there will be some math later on. And then finally, I'll go to a coding project that I started essentially to replicate one of these papers in PyTorch, and ultimately, I hope, if I ever get back to working on it again, be kind of a repository for generalization research and generalization algorithms. So we've all heard of machine learning. It's in everywhere, from your Netflix to your self-driving car, your Waymo, fraud detection, language models. Everybody is all over language models. By the way, if you don't know Hugging Face, I highly recommend checking them out. They're awesome. Clem is also on Twitter, so I recommend following him. He's the CEO. But yeah, there are tons of companies that do this. I think this was like a venture capital report of all the companies doing machine learning and deep learning in 2019. And then this is what it looked like in 2023. And I'm pretty sure the number just continues to grow, especially with this boom with large language models. I don't know if my company is on there. I'm not going to try to find them. I hope. Well, my present company is not, but probably Black Sky might be somewhere. Unfortunately, when deployed into production, the models sometimes don't work. Sometimes the self-driving cars crash. Sometimes you get models that end up with algorithmic bias, and this is a central problem in machine learning, where models that get deployed and work on generalized data might not have the same kind of behavior that they will in training data. Solving this problem is a really big issue in research, and it's still being worked on, and I'm hoping I can make like a tiny little contribution to that. But yeah, the fundamental idea of generalization is we want to know how our models will work in the real world when they encounter data they've never seen before. Now, in what is known as classical machine learning, and when I say classical machine learning, there was a theory that was developed to try to predict how this worked, and I'm going to take a brief overview of machine learning and why that theory is important. So I'm going to begin just with a basic idea of what machine learning is. There are typically two types of what are known as learning problems. There's the regression problem and the classification problem. I think the regression problem is the best one to start with. What you do is you'll have some kind of function. This is known as a target function. This is like the ground truth or the real function. You will, from this function, sample some training data, or you make an assumption about the function. Typically, this will mean that the function will be covered by two variables, omega and a bias variable b. When people talk about weights and biases, that's what they're referring to. This omega variable will be attached to the inputs of the function, where the bias variable is regardless of the inputs. It's just kind of like there. It just moves the function up and down. From this training function, you will get some training data. In the real world, this is like taking pictures of cats and dogs, or taking pictures of the world. People are talking about GitHub. This is them reading your GitHub repo, of which all my repos, I don't care. It's on MIT license. You can do whatever. um, then you only look at your training. You only look at your training data because that's what you have access to, and you propose different hypothesis functions. Using a learning algorithm, which I won't get into, you find a way of selecting the most relevant hypothesis function, and typically this will be the hypothesis function that best fits your training data. And if you remember back to the original function, the hope is that your final hypothesis function is similar enough to your target function, right? It's a So that's if you're doing regression. Regression means that you take some input variables and you have like a number. The other type of problem is classification, which is actually what I'm going to cover. And I think this is the much more simpler problem. It's the much more fun problem, although it's the less useful problem. Even though some would say even some of the most complicated models are just really big classification models. In this case, instead of having a target function, you have a target space, and the target function just cuts off the space. On one side, you'll have the function will characterize variables in one way, and on the other side, it characterizes variables in any way, and in another way, right? And your training data can lie in any space of this function. Or any part of the space. This means that your set of hypothesis functions is not just a straight line, but it's actually a greater than or less than, right? So you'll be classified on one side of the function if you're greater than it, and classified on the other side if you're less than it. And that's kind of it in a nutshell. In the real world, these functions are nonlinear in high dimension, but this is just your basic idea. And similar to the regression problem, you will also sample your training data, you propose a set of hypothesis functions, and you pick the best hypothesis function. Note that sometimes you don't always classify the data points correctly, right? Sometimes, because again, this is a hypothesis function, you might get some of these red points here, which are misclassified as blue points. If you know any machine learning kind of characterization, this will appear as a false positive, false negative, or this will be your sensitivity or your specificity. That's typically what this is caused by. All right, so that's machine learning. Yay! Unfortunately, it's not so simple because we can define our set of hypothesis functions in different ways. In particular, what we can do is choose the number of parameters to define the set of hypothesis function. And since we don't know the target function, we want to pray that the set of parameters in the hypothesis function is the same or similar to those in the target function. So let's imagine we have some target function that is some kind of curved line. So you can imagine this won't be a simple y equals mx plus b. This might be like a parabola or a quadratic. If you sample from the training data and then you try to make a linear function which only has two parameters, you won't get a good fit, right? You won't get a variable that approximates your original target function. So you might think, okay, I'll just add 8 parameters. Maybe that'll work. But unfortunately, you can run into another problem of overfitting. Notice how in this example, all of the training data will get fit, but you're still not having a good approximation of your target function, right? So this is known as fitting to the noise because the data gets sampled with noise. And if you have like a too powerful function, then the noise will start to cause errors and you cannot generalize properly. This is the reason why a lot of models in production fail. So the key is to get your hypothesis function to be just right, that it closely matches your target function. And you can kind of use some intuition, like you can think, what is the space of hypothesis functions that might be what my target function is, or you can just guess and like try a lot of parameters and do a parameter search and run up your AWS budget.
So, Elliott, with the overfitting situation, you were mentioning earlier that you were on some social media app or something, doom scrolling per se, and maybe you lingered too long on a particular video or gave it feedback, and then
Mm.
it's you said the algorithm seemed to be gaslighting you. So, oh, you like that one thing? I'm going to show you exclusively that from here on out. Is
I
that
mean,
an example of the overfitting in the wild?
the goal of the app is to get me on the app, right? So I typically no. So
Okay, so that's
that's the
working as intended.
yeah. So a lot of times overfitting is thought of as memorizing the training set. So let's say you show it a set of images of cats and dogs, right? And the images of dogs only contains Dalmatians. In fact, actually, a better way of thinking about it only contains the dogs in your neighborhood. And you have many of the pictures of the dogs in your neighborhood, so that when the model sees a dog in your neighborhood, it's like, I know exactly what that is. Because you've basically fed it a training image, right? But if you feed it any other kind of dog, like maybe there's a Chihuahua or a Schnauzer or something, well, yes, that would be a dog. But the model will be like, I've never seen this before, right? This isn't my training data. So a lot of times, what you have to do to prevent overfitting is you like nerf the model, right? You say, okay, don't look for specific images of dogs. Look for like lines and eyes that are certain widths apart, or look for like generalized snouts. And and that will mean it's going to get some images wrong, but it'll still see an image that's like a dog it's never seen before, and it'll still maybe recognize it, right? Because it has enough fuzziness in the model to be able to look at data points it has never seen before. And again, like getting an intuition with overfitting isn't always the easiest because you have to think in terms of what the machine is thinking. But yeah, it kind of comes with practice. I'm trying to
No,
think of other more salient examples of it. um, okay, let's continue. I don't remember what my next slide was. Oh yeah, this is just an overview of scikit-learn. There's actually a screenshot from scikit-learn that shows different levels of overfitting.
I could give Elliot. I could give you an example if you like.
Sure.
Sure. So if you have a database of whatever salaries and people's zip codes and names, and if you train on serious stuff like say that you decide that the first two letters of somebody's name are indicative of their salary, predictive of their salary, that's not just overfitting, but overfitting to something that's obviously spurious. But in general, you don't know. The more variables you throw at the thing, the more complex the formula you come up with, the possibility of overfit is higher. You want the minimal formula that explains most of the variance, and you can look at the knee of the R squared curve or whatever goodness of fit.
Yep, that's exactly very well said. You want the minimum number of of weights to describe a proper model and no more. You can see some examples of this where these are different decision boundaries in scikit-learn. Notice the ones on the right; these are all underfit. The ones on the left are all overfit. And the important thing to learn to make note of is this is classical machine learning where the performance will degrade when you add too much parameters. Now, some of you might be scratching your head. I have a brief mention of support vector machines. These are a special type of machine learning models. All you need to know is the way they get around the overfitting problem is they try to maximize the boundary, right? So if you have some kind of classification function, then you want to maximize the distance of that classification function to your training debt. This causes you to isolate training points close to your decision boundary, and those are called support vectors, and that's why they're called support vector machines. Okay, so deep learning should follow this problem, right? Right? Yeah, right? Except let's think about this. Some of these deep learning models have millions of parameters. Some of them have billions of parameters, right? I think, what was the one machine, XAI Colossus or something? It has 100,000 H500s. This is what happens when you have a bajillionaire, we have more money than God. So wait, why are these models not overfitting? Shouldn't they overfit? And this was noted before these big LLMs. This has been a noted problem forever. One of the first papers to make note of these is this one by Zhang et al., which states understanding deep learning requires rethinking generalization. And they made this observation that even in the case where the training parameters are greater than the number of samples, the test error and the train error can often still be small, right? So test data or the performance in test can match the performance in train. Sometimes it does, sometimes it doesn't. And the question is, well, when does it do that? They did a bunch of experiments where they trained a model on train data, and they found that depending on what parameters they used, they could get test accuracy to closely match train accuracy or test accuracy to not match train accuracy. And that's what's really important here. The train accuracy was in no way indicative of the test accuracy. So it's like, okay, we need to find some other, and this is with the same number of parameters, right? So varying the number of parameters does not, for deep learning models, does not predict test accuracy. Womp womp. That's really bad. So how do we predict test accuracy? One thing they discovered is that one thing deep learning models do is, going back to the support vector machine, is inside the model, they actually make these little support vector machines where the decision boundaries will maximize the margins. They actually did a derivation of why this occurs. I won't go through that derivation, but just like, trust me, bro. So what if we could measure this margin per se? Wouldn't that be great? So luckily, so there's implicit regularization, which means there should be a way of measuring these margins. This is just my meme, And classical to statistical learning, we learn our VC dimension and we get some experts, but deep learning, we just stack more layers, bro. Let's just go.
More layers.
Yes, more layers.
Share the pile.
So we want to be able to find this generalization bound. This means it should handle any FIB4 network. It should measure properties at any layer and be robust to outliers and be computed from training data. But I've discussed before, maybe there are these margins in these deep learning models that can help us figure out how well they generalize. In this paper, they kind of develop a formula to try to figure this out. This is basically just the definition of a decision boundary. Essentially, it means that for any set of training data, there are multiple functions for each class. And if that function is the maximum, then it classifies to that function, right? So if you have a function for cats and a function for dogs, and your cat function is a 1 and your dog function is a 0.2, then it's a cat. In the instances when the training data has the functions equal to one another, so if you have a data set and the cat function says 0.5 and the dog function says 0.5, that is your decision boundary. Hopefully you should not have that function. Hopefully such a thing does not exist. I don't want to think about a cat-dog hybrid, Consequently, one way to get a distance of a point that's not on the decision boundary to the decision boundary is you define this decision boundary, you compute the distance, or you compute the distance as the minimum displacement that results in a score tie of the function. For those of you that are physicists, you might notice something. What happens when we set up something as a minimum and then take the limit as that minimum approaches 0? What you do is you get a Taylor approximation. So setting up the decision boundary in this way allows us to create a Taylor approximation, which means now what we can do is, if we want to get the distance to the decision boundary, all we have to do, and this is the meat and potatoes, is all we have to do is get the intermediate representation of that function for the different classes, and then the square of the gradients. And the cool thing is that both PyTorch and TensorFlow allow us to compute the gradients and the intermediate representations. Well, actually, TensorFlow is way easier. PyTorch, oh my god, you'll see later. PyTorch is not that easy. It literally took me months to figure out how to do it. But you can do it. Okay. This is just a normalization. All this is if you want to compare margin distributions, this allows us to get a margin distribution. If you want to compare the distribution of margins between each layer, you just have to normalize them. And all that means is you take the distance of every point to the mean of all of the points, you square them, and then you take the square root, right? And that gives you a normalization constant. I've tested it and it works. And it allows you, what it does is it causes the margin distributions to be very well behaved and to be comparable to both one another and also like within models. This is not that important, just know that it's there. Now, what do these margin distributions look like? So in the paper that Zhang did, they trained models that had different test accuracies, but the same training accuracies. And they found out that when you get distributions of margins, again, these are the distance of the training points to the decision boundary, when the distributions are thinner, the test accuracy is worse. When the distributions are thicker, then the test accuracy is greater. And you can kind of think of what's happening is these margin distributions or these internal decision boundaries are like self-correcting, so they are the furthest away from the training points. So that if there's any kind of jiggle in the training points, then they will still be captured by the decision boundary. But basically, thick is good. Sorry. I was thinking of the Aku meme from by Jack. Oh man. So this turned out to be very effective. They had trained several margin distributions. They essentially got a goodness of fit for the thickness of each distribution, and that matched very well with the training data. That's what this is in the left. On the right is an older type of generalization bound that didn't work very well. Okay, yay, we solved generalization. This is my favorite character from anime, Tieria Airday. You know, he speaks to the machines. We can speak to the machines now, right? Except, no, they leave us on read. Because, unfortunately, these margin bounds are kind of limited. You have to do experiments with multiple types of models. They only work within certain families. And they still aren't perfect. There has been subsequent work to kind of build on what Zhang did. And it's still kind of an ongoing field. But unfortunately, this was a field that was, this is just an application where they trained a model, they actually degraded a layer, and they found that degrading the layer can change its margin distribution, which gives us an idea that that layer is the one that was being affected, which can, help with layer design, architecture design. So that definitely is some use case to this type of research. This later on, they created a competition of which when I release the slides, you can go find it, where they essentially released a bunch of pre-trained models, and a bunch of training data. I think it was on the CFAR 10 dataset, and no, it wasn't on the CFAR 10. Yeah, it wasn't. Okay, don't quote me, but it was on some training dataset, and it allowed you to make different margin distributions, of which you can go play with. They're all there. A lot of the winning contestants were created, except it was done in TensorFlow. And if you know the machine learning world, no one uses TensorFlow anymore. TensorFlow is great. It's done a lot in production. The research world has largely shifted to PyTorch. So I took it upon myself to start converting all these algorithms to PyTorch. And that leads me to my current project, which I dubbed PyTorch Generalization. I know that seems kind of self-aggrandizing, but whatever. It's GitHub. Everybody has it anyway. In this code, if you remember the equation from before to compute the margin distribution, I coded that. I actually think it'd be better to just show you the project. So yeah, this is the repo that I created. And if you go to scripts, margin distribution tools, I kind of do a step-by-step on how we get these margin distributions. So first what we do is we get if you remember this equation, we get the numerator of it, which means getting the different internal representations of the function for each layer. How you actually do that in PyTorch is actually kind of wild. What you have to do, so these two functions right here, they get the indices of each one of the layers that corresponds to each class, right? So that's why the number of the class is here. And it gets passed to a one hot function from torch, which creates a matrix of like ones and -1. Notice that gradwise in this case subtracts. That's because you're essentially subtracting these indices because you want to add the function from one layer and then subtract it from another layer. Or sorry, you want to add the function from one class and subtract it from another class. Then you get the internal representations. Now, this is actually really interesting. This literally took me like 2 or 3 months to figure out. You have to like register each one of the neural network types. So I have linear, flattened, max pool 2D. And then when you run it, so when the model gets run through, it will register the internal representations, and you can then pull from them and use that to construct your numerator, which I believe. Oh yeah, that actually happens right here, but this will get populated when you run through this section, right? You can also construct your denominator. You see how there's like a torch.square root.sum. So this is the autograd function. So this is the function that computes the grad. These layer dims, these are constructed from these matrices right here. I believe that comes from. Actually, where did that come? I know they're somewhere. Oh yeah. So for each, when we go through, when we compute the autograd, we feed the grad the indices for the classes we're going to use, and then it runs through the autograd, and then that gets multiplied and summed on this line. So that is this denominator right here. Going line by line, figuring it out. Took me so long. I actually was in a coffee shop doing the vectors in my hands. Finally, we construct a margin distribution by just doing my favorite thing to do with PyTorch, where you like send it to the CPU, you detach it, and then you send it to NumPy, just because NumPy is awesome. And then we make a Python dictionary. We clean up all the hooks that we attached in order to get our intermediate representations, and then we're done. Now, it's important to return the intermediate outputs because we need them for computing the normalized margin. That's what this portion is. I'm not going to go through the normalized margin. Just know that it's all done in like NumPy. But yeah, that's what this is doing. Is it's computing the normalization constant. I actually have some additional things here. In order to attempt to replicate the work of the PGDL competition, I made a TensorFlow to PyTorch converter, which doesn't exist. So I just made it. This is not a generalized converter. This is a converter for the specific format in the models. I think it'd be a wonderful project if someone was to take this and make a generalized TensorFlow to PyTorch converter and also a PyTorch to TensorFlow converter. I don't want to do that. Maybe one day I will. But yeah, the most important thing about this, most of this I think is just pretty basic. You just copy the weights, you feed them into a PyTorch model. But the interesting thing is that PyTorch has everything in channels last, and TensorFlow has everything in channels first. And trying to figure out the matrix transpose, because you have to transpose with the indices of the different tensor, because it's a rank 4 tensor, right? You have batch size, x, y, and number of filters, because it's a convolution, so it's like a 4-dimensional tensor. Was just like wild, and this like took me so long. I actually just eventually I just said screw it and I brute forced it. But yeah, that was probably the most difficult thing to do. And then that's how I made a conv layer. In practice, what this looks like you doing is, okay, so feed. So in practice, when you're converting a model, all you have to do is get the model in the specialized format from the PGDL competition. You feed it into the CT model as a TensorFlow model.
Your code or your text, it's a little tiny.
Oh yeah.
So much better.
So
a little bit more would be a little better.
Okay.
That's
Elliott, before we go too far, are you doing this layer by layer in terms of getting the margins? Like specific?
Yeah. The margins are computed for every layer, and the models are converted for every layer.
Okay.
And that's actually the powers that you essentially get to introspect into what each individual layer is doing. Right. There's some other stuff. There's some meat and potatoes. I made some GitHub issues. I'm currently in the process of just like making this not my personal thing into its own project. So just be on the lookout for that. I'm probably not going to modify this project anymore, but I have some ideas of where to further take it. Obviously, I have to finish replicating what they did in the paper. There are a couple of other generalization algorithms. The model, I currently cannot do dense layers, so that's actually a really big one, is computing dense layer margins. The paper didn't do that, so it's essentially, it would have to be done independently and tested independently. And then also some Jupyter notebooks and some documentation. And I think that's almost everything. Oh yeah. So I've already done some so just some note on PyTorch and TensorFlow. This is just saying that PyTorch is more Pythonic and it's more popular. TensorFlow uses gradient tape. PyTorch uses autograd. So this is what. So in my own experiments, this is what a normalized margin or an unnormalized margin looks like for the Minis set. And you can see that this can be calculated for different layers. And because the actually, I'm actually kind of surprised that unnormalized, they still look pretty similar between sets, between layers. And I think that's it. Yeah. If you want to, this work is continued. If you want to look at some other papers that I recommend, this one I actually really like. Okay. Deep learning researchers love to do this. There was a paper called "Fantastic Generalization Measures and Where to Find Them" in reference to the Harry Potter book "Fantastic Beasts and Where to Find Them," and then someone kind of made like a counter paper saying "Fantastic Generalization Measures are nowhere to be found." It's not that pessimistic, but they're both worth reading. And there's even some work to kind of move this to provide generalization bounds for large language models. I wish I had more time to go into this, but this paper is definitely worth reading. I've kind of glazed over it. And yeah, that's it. If anyone has any questions?
Yeah, Elliot, I'm just curious. You went over some figures that from the papers, and I wanted to figure out which ones were Zhang's papers and which ones were Jiang's papers.
So all of these were from Zhang.
Oh, okay.
Yeah, so this guy Yijing Zhang, he actually, it's funny, like we follow each other on Twitter, and he retweeted this. He's a Google researcher that kind of did this. I don't know Zhang. This is like the impetus. I think he's one of Sammy Bengio's students. But yeah, this is the much older paper.
Okay. So once you calculate the margins, how do you then is that just directly transferred to a measure of generalization?
Yeah. So they go over this in the paper where essentially what you do is you look at how thick these margins are. And there's several ways of doing it. Like the easiest is you just kind of see where they go to zero. You have some kind of minimum threshold, and that allows you to figure the threshold, the thickness. You can also make a box plot and look at the distributions within certain percentiles of the margin distances, and that can also kind of give you a rough approximation for the thickness. But the thicker the margins, the more likely they are to generalize. Oh man, quiet.
Well, I mean, aside from that, do you have any insights on the proof of that this is actually why it does the generalization?
Well, it makes intuitive sense. Because if you think of how training data kind of comes, so real life data comes in with some jitter, right? So like when you take a picture and then you look at it in the real world, a similar picture won't look like your picture in the training data, right? It might have a different angle, or it might have different colors might be shifted. And you can think of that as being similar to the training data with some noise, which means that it should still be correctly classified by your decision boundary, but it'll be farther from it. So if your decision boundary is smooth, right, and it doesn't have as many variations, then noisy training data should be better classified, right? It's like the margin is almost best thought of as like a slack or a like a like some I mean, I'm trying to like the word escapes me, but some leeway in terms of how well your model can perform. And that happens, and the way you can find that out is when it is the maximum distance from your training data, right? So if a point has a tiny little deviation, it doesn't get misclassified. It doesn't kind of go across the decision boundary.
Okay. Yeah, that part of it I think makes sense from the support vector machine intuition.
Yeah.
But in terms of like how you mentioned it's kind of like taking the minimum of a particular function. Can you give some?
The margin is?
Yeah.
Yeah. So when it's in taking the it's more of like taking the maximum of a function, where like the maximum is you want all the distances to your decision boundary to be maximized.
Okay, and then that turns into a minimum of some other function, some inverse.
Yeah. Oh yeah. That turns into it turns into a maximum accuracy, but I guess a minimum misaccuracy.
Okay, I understand. Yeah. Okay.
Yeah. Yeah. I guess if there's anything that's minimized, it's the deviation from your test accuracy. Maybe I can draw this out in Paint. Actually, I don't know. That might be a little bit involved. Oh, wait, I can annotate it. So let me go back to this one, right? And so the I sort of think about it like this. If you have some kind of like wiry decision boundary, right? And maybe it gets really close. But it wasn't so this is actually kind of cool because like, oh yeah, okay. So here's the thing. This is based off the training data, right? Notice that this decision boundary is going to be very close to the training data. How do I? Okay. But it completely doesn't approximate the original function, right? So if I draw like another point, so this is blue, it will be this is correct from the original target function. These functions are correct, right? From the original target function, but because the decision boundary is so wonky, it gets misclassified, right? If these points would be misclassified as red points, even though they really should be blue points. So if you want to get the sort of like the most correct decision boundary, one way to do it is you just try to make it the maximum distance from all the training points. It's like, I don't want to touch you, training points. And then it's going to a lot more closely approximate your target function. That's sort of how I think about it.
Okay, yeah, that makes sense. I think you had a slide on before you did the Taylor expansion where there was a minimum of something.
Oh, you know what that was? That was probably the that might be this one, right? Where you want the test error minus your training error to be small. Oh, I know the one you're thinking. You're thinking of this one, right?
Yeah.
Yeah. Okay, so this is based off of the this is okay. This one actually confused me because I think it's actually written a little bit weird. What it's saying is that let's say this is a decision boundary, right? And this is a data point. Can I make this a different color? No. So these are all the potential distances, right? And that this little delta is like the deviation of the distance from the minimum. So what we're trying to do is minimize the deviation to the minimum distance to the decision boundary. So that's what this does, right? It says I think the weird thing, and I think they wrote it weird. I should probably send them a message about this, but they're trying to get the distance to the decision boundary, and that distance is calculated by finding the minimum of all the possible distances to the decision boundary.
It's kind of like finding a stationary point of the distance, essentially.
Yeah, yeah. It actually reminds me a lot of like the many paths from quantum mechanics. That's sort of how I saw it.
I was thinking of like the path of least action type of thing.
Yeah. Well.
Yeah, if you say it's a hyperdistance in n space and you're picking the shortest one.
Yeah. And the nice part is when you take things as short distances, then you get to apply Taylor functions. I haven't done the Taylor expansion portion of that. I'll leave that as an exercise for the user.
Well, I mean, it assumes your decision boundary is smooth and all that.
Yeah.
Which it may not be.
Well, ideally it should be smooth, but yes, it may not be smooth. Which might actually be that actually is pretty interesting, because that might be, I should actually write that idea down, because that could, I should go to the chat. That could be a limitation on the effectiveness on how they're computing the margin distributions. Cat, what about features, e.g. x squared is in this case? Oh, I don't know. Oh yeah, someone posted the paper. Cool. Is it done through derivatives? If you're referring to the margin distribution, yes, it's done through derivatives because you take the gradient.
Nitin was wondering if that's the paper that you were reciting.
Yes, understanding deep learning requires rethinking. Actually, I don't know. Wait. Yeah. Qiyuan, yeah, that's the first paper. And then Yi Jingxiang, yeah, that's the second paper, and that's Semi Bengio, who is both of these are the correct papers.
And then Woody cited the second one. Okay.
Yeah. Yeah. If you go to this paper, I'm much more familiar with the second paper. That's where these figures are from. That's where they do the derivation of this third equation, was like the big one. And then they go over their methodology on how they tested and like confirmed that it was correct. This is a wonderful paper, and as is some of Zhang's later papers.
So can you use these insights to make these language models or vision models actually better architecture?
So that's the hope. So this paper here, essentially kind of did something akin to that, where they found that you can kind of figure out which layers are degrading, which ones are the ones underperforming. This could allow you to test hypothesis blocks about hypotheses about how you're constructing your models. Truth be told, there are actually some better algorithms for doing this that I later discovered. There's this one called Weight Watchers, is like way better. So well,
this looks like it's a third paper.
Yeah, this is a third paper. But in this paper, I think I cited this one because they actually applied margin distributions to kind of figure out how models are performing.
That's okay. I've got a screenshotting tool, so I screenshotted the URL.
Yay! But yeah, this is one of my favorite ones. It's funny. Sometimes you'll like look at the papers that will cite these, and they'll just be, oh, this thing exists. But this paper actually used margin distribution, so I thought that was really cool. And I've been in talks with people. So the way language models work is they have a slightly different architecture where they use attention blocks, but they also do have an internal dense network, which essentially does a classification problem. So you could theoretically apply this to language models. That's like one thing I would like to try, just to see how well it would work. I have no idea if it would work well, but I would think it'd be cool if it did.
Well, you can imagine that as far as the embeddings themselves go, having some good margins between particular concepts that tokens are embedded in could be a very similar sort of thing you could do in large large language models or any sort of interpretation type model.
Yeah, I think that's a wonderful idea. For the, like when you're trying to do an embedding to put them in like a vector database or something.
Yeah, something along those lines.
I should write that down. Alexa, turn on bedroom lights. I will write that down. I don't have my pen on me. Oh, here's my pen. Is it okay if I write that down? That's a really good idea.
Yeah. I think Woody's recording everything.
Yeah.
Margin. Cool. Yeah, that's all I have.
Awesome. Well, it's past 11 o'clock where Elliott is, so appreciate you being willing to stay up late and show us what you've been working on. And thanks for all the great questions, everyone. But this is your last chance before we let them go for the evening. Anything else for?
Yeah. How can we connect with you?
I prefer LinkedIn the best. I also am on Discord too. But yeah, LinkedIn, find me. I think my LinkedIn is.
I put the link in the chat just now.
Yeah, hit me up on LinkedIn. That's where I talk about things professionally. I'm also on Twitter, and I try to stay well behaved on Twitter, but sometimes it's hard.
Question for Elliott.
Yeah.
When you basically that you mentioned TensorFlow is used in production, but is that like internally at Google, or do people outside of Google use it not in production?
So
like, to what extent is PyTorch taking over?
Yeah, so it's funny. I really wish I had the slide. I actually, so I've given this talk many times, and I actually did have a slide that addressed this. But so TensorFlow was essentially the first one to come out, although I do think Torch was also out around the same time, but not necessarily PyTorch. And because of the early creation of TensorFlow, that caused this like mass adoption, right? So for a good like 4 to 5 years, TensorFlow like was the thing. And in particular, it heavily percolated in industry. Industry has the problem of if you use one library, you kind of have to use it forever, because then you could accumulate technical debt if you do a conversion. So
yeah, I mean, people got locked in early. Sure.
Yeah. The research community is much more malleable. So when PyTorch came to the scene about 4 or 5 years later, and got really mature, the research community just heavily adopted it. So if you go to like papers with code, almost everything that is new and current is in PyTorch. Sorry.
Right. I'm just curious about the sort of competitive dynamic. Why it seems like Google has abandoned any idea, like why everybody in the community is okay to let PyTorch be the de facto standard.
I mean, PyTorch is good. Although I will say, in doing this project, I kind of learned of the ins and outs of both. I think TensorFlow. So in my experience, TensorFlow is very rigid. It gives you all these weird errors. It's very annoying to actually construct a model in TensorFlow. I did find that getting the gradients and the intermediate representations was way easier in TensorFlow, whereas PyTorch, everything is much more Pythonic. It doesn't error as much when you're trying to construct a model, and the errors like make sense. The other thing I love about PyTorch is that it's much more granular where you put the data. So you can define like a device in PyTorch, and you can send things from the device or take things from the device. I think it's better with dynamic graphs, but I've never used dynamic graphs off the top of my head. Yeah.
No, sure. I meant not so much TensorFlow versus PyTorch. Like I think TensorFlow is history what people started to say. PyTorch versus anything else. So some people use FastAI on top of PyTorch, which is sort of simplification there.
Yeah. I tried FastAI. I didn't really like it, but yeah. The one thing I did actually was forced to try and use it at Black Sky because they made everyone use it. PyTorch Lightning is kind of sort of seen as like the next thing in that it's supposed to be PyTorch without the boilerplate. I personally don't like it though. I think it solves a problem you don't really need to solve. So yeah, I'm happy with PyTorch. Although if you're in the language model space, there's a lot of like Hugging Face, like Olama and like LangChain and stuff that abstracts like everything.
Sure. Is your stuff specifically just language, or are you doing like image, audio, all the other stuff?
So right now, everything is optimized for images. All the training data sets are for images. theoretically it could be done for any data set type that is classification. I don't think it could be applied to regression. Although a lot of like regression problems can be cast as classification problems. So for example, if you're doing like next token prediction, that's theoretically, like technically it's a regression problem because you're getting probabilities for each one of the tokens, but in practice it's a classification problem, right? Because you're classifying what is the next token in a bag of words vector from the previous token.
Sure. Okay, thanks. Thanks for your talk.
Yeah, thanks, Elliott. Awesome talk. You are welcome.
Thank you.
You are welcome in the future to come back and update us on your workings in this space. This is great.
Yeah, hopefully I can finish my job soon. I'm actually like I might get like an offer letter for a new job. Yeah, I haven't worked on this for 3 months, so I'm like really excited to get hired so I can work on it again.
Awesome. Well, I'm happy to cut out any of the job talk from the recording.
Okay.
All right. Okay. Well, hey, that's work for me. All right. Well, thanks again, and thanks everyone. We will see you again in a month.
All right. See you. I'll stay visible in case you want to see me again. Have a nice day.
Awesome. Yeah.